that E can also be uh, written in terms of gradient. That is, E is equals to negative more grad de V. Then this V is known as the potential electrostatic. So I might bring you a question amongst the question they could the first part. I might tell you to give me the relationship between E show electrostatic, A potential electrostatic. Okay, V is the potential electrostatic. Okay, and then so far we've established that E is equal to, if you remember, 1 over 4 pi epsilon 0. I might ask you to give me the formula for E with a charge Q. Okay, and then the vector OM over its magnitude to the power 3. Okay, we learned how we came up with this formula according to Coulomb. Okay, then V is not a vector, V is a scalar. Okay, this potential electrostatic is not a vector. It's very similar. These formulas, you find that when you're studying these formulas, the way you'll be studying them, they're very closely related. So for V, it's just Q over 4 pi epsilon 0 with, because it's not a vector, OM, which means OM, which is the magnitude. Okay. So when you're being asked to find the show electrostatic, sometimes it's easier for you to find the V, which is potential electrostatic. Then once you find your V using this formula, so as you can see, these formulas are like closely related. Once you find your V, then you can just apply this. E is equal to more grad de V. Okay, and then how do we find gradient? Okay, you should look at one. We should watch one of the first sessions if you've forgotten, but I'm going to remind you. It's going to be pretty. It's not going to be difficult. So now today, let us look at one of the possible questions that can come in an exam or something similar to it. Okay. If you follow nicely, there's just a bit of mathematics. Of course, I'm going to help you with I know you're new to a certain way of solving things, mathematics and things like that. So I'm going to try to just follow the steps, the way I'll be doing it. If you follow nicely, you'll find that it's actually and easy to understand. Let me go all the way. Where are we? So yesterday, last week we were solving this question. We're solving a question. This question. Show créé par un plan. Oh, show créé par un disque. Okay. Show créé par un disque. They were trying to, this is show electrostatic. They're asking you to find the E that is created by a disk. Okay, a disk which is uniformly charged, and it has got charge density, so surface charge density. Okay, so today we're going to try to study show créé par un plan infini uniformément chargé. So I'm going to describe what a plan infini is before we even start solving, and then how to go about it. So how to calculate the show electrostatic? There are a lot of methods. Okay, there are a lot of methods that we can use to calculate the show electrostatic. Okay, one of the method is called the calculate direct. That is direct calculations. Okay, in English, direct calculations. That is, you use the formula, you simplify that formula, you go with the mathematical calculations, you go with them. Then this one, you use the concept of symmetry. Of course, symmetry is very important. It simplifies the calculations. Then the other one, the other method is via through, not me saying via in French, through the relationship E is equal to, this relationship is a very fundamental relationship, gradient of v. So we can also use this relationship to find E. Then, yeah, and then there's another method that I use, the simplest to me, but yet difficult for you who are still new to the system, which is using solid angle. Of course, solid angle was a whole topic last time. So now we're going to, yeah. Then we can also use theorem de Gauss. We looked at theorem de Gauss. I'll remind you again. Theorem de Gauss Actually, I'm going to start with theorem de Gauss, and then I'm also going to use now calculate direct. Then I'm also going. I'm going to use both of the formulas. So I might give you like might the exam, they might ask you to use one of the formulas, especially the first one or this one or this one. The solid angle one is just from my school. We used to use the solid angle one, and it's the simplest one. So I'm going to, I'll be forced to give you all the methods, but you're just going to be doing the same thing. So I'll be forced to give you all the methods because in your schools they might specify the method to use. Okay. And there are other methods that people can think of, but meanwhile, these are the most common methods that you can use. Okay. So now, going to our question. Okay. So no, where am I? Yeah. So we're going to use the theorem de Gauss, but for you to use the theorem de Gauss, you have to you also have to apply a concept of symmetry. Okay. So yeah. So on considérait le plan infini z is equals to 0 pour toute la charge sous-pacifique. This term is very important. It's called sigma in Greek. Sigma. So la charge sous-pacifique uniform. So then here they will specify the coordinate system that we're going to use, the x, y, z coordinate system. So the first question is, de quelle variable dépend le champ électrostatique? So to begin with, we're going to use symmetry to know which variables our show electric they depend on. So this is the first question. So this is the method of theorem de Gauss. Before we even begin, we have to know which components we're going to use, which components. Okay. So plan infini. What do I mean by plan infini? It's an infinity plane. Okay, where z is equals to 0. This plane is x or y plane. Is that a question? Okay. An infinity plane, you are going to be asked to calculate the show electrostatic or an electric field, an electric field created by an infinity plane. So when z is equals to 0, what we mean, it's an x or y plane, and by this is a plane, an x or y plane. Okay. The drawing is not good. This is a plane. Okay, so what do you mean by an infinity plane? It keeps on going in all directions. Okay, it's infinity. Okay, the plane is infinity in all directions. Okay, that's what you mean by plan infini. So this is uniformly charged. That is, it is a continuous distribution of what? Of charges, point charges. Okay, so these charges will create a show electrostatic. Okay, to begin with, we'll create a show electrostatic. Yeah, so these charges will create a show electrostatic. and then and then um, so to begin with, you're going to study the direction, okay, the directions of your show electrostatic. So the show electrostatic is a vector, an electric field is a vector. So if you're using the Cartesian coordinate system, so it's going to have what basically what we mean is it's going to have different coordinate systems. It's going to have the component in the x direction, the component in the y directions, and the component in the z direction. Now, so for you to find the total show electrostatic created by this plan infini, you have to calculate each component according to the coordinate systems. For example, if you are using the cylindrical coordinate systems, which uses rho, phi, and z, if you remember from the topic of coordinate systems. Okay, so which means E will have the component in this coordinate system, phi plus the component in the direction of phi plus the component in the direction of z. Okay, now the concept of symmetry is for us to get rid of some components, because some components you find that they are zero. For example, for plan infini, the only component which is valid is the ez component. That is, this is going to be zero, this is going to be zero. So our E is equal to Ez. Okay. So now this question, to answer this question that was asked, decade variable depend the show electric. They mean from these three variables according to the coordinate system that I've given you. So I might ask you this question as part of question I might ask you this question. So which variables does the electric field depend on? So it's a z variable. Okay, z variable. Then what is the direction? That is it in the x direction? Is it the y direction? Is it in the z direction? Okay, so we're going to see how if we determine that it's in the z direction. Okay, now before I go any further, if we so basically what we do is um do I have a picture? Okay. Do I have a clear picture? Okay, let me use this picture. No, let me use another picture. Let me use this picture. Okay, so we consider this is an infinity plane. If you're able to see it, this is an infinity plane. So we consider an infinity plane. It keeps on going in all these directions. So it's infinite. So it's not just represented here. So now this is what we call a disk. Okay. So we're going to do two questions actually. We're going to study the show electrostatic created by this disk. Then we're going to study for now we're studying the show electrostatic created by the plan infini. Okay. Now by definition, the plan infini is just considered to be a disk. A disk will have a radius of r. So this is the plan infini is considered to be a disk where radius approaches infinity. Okay, so the plan infini, this is the representation. So for the we consider the plan infini to be, so if you're able to do the calculation for a disk, just to say when r is equals to infinity, what will be the answer? So when the plan infini is also considered to be a disk with radius up to infinity, because if the radius is going to infinity and for the plan infini this is going to infinity, so it's going to be the same. So from here we can say that uh, plan infini is equivalent to what? A disk with with radius of what? Radius that approaches infinity. We can say, if you want, you can say radius equal to infinity, but we're not mathematically we're not allowed to say that. So radius approaches infinity. So the term that we use is radius approaches infinity. So basically, if I'm able to calculate the definition of show electrostatic for a disk, okay, for example, the answer will give us maybe, let's say the answer gives us sigma over the radius. Then I'm just going to say what is the answer when radius is equals to infinity. I don't know if you've been learning this in additional math. This sigma is constant, so sigma over infinity is equals to 0. Okay, so if the answer gives us, for example, I'm just giving an example. If the example for a disk, if the answer gives us sigma is equals to radius, sigma over radius, then if I were to ask you to find for the plan fin, you don't need to do the calculations. You can just deduce the answer from for a disk, because we know that a plan fini is a disk is equivalent to a disk with radius equals to infinity. So in your answer where there's radius, the answer will have radius for a disk. So where there's radius, you put just put infinity. So for this case, it will be 0. I don't know if that makes sense. So what I'm trying to say is you get you can calculate. I can give you a question to calculate the one for a disk, then tell you to deduce the one for plan fini. Okay, that's another way you can find for the plan fini. But at the moment, we're going to assume we haven't calculated. We haven't calculated for the disk. We're just going to calculate for the plan fini. Okay, so if we have a plan fini, okay, so um, well, let's go back to the concept of symmetry. So there's what we call principe de Curie. It's not important, but what it says is that it helps us determine the direction, which components and which directions where show electrostatic would depend on. For example, you can use principe de Curie. This is where we use symmetry. Well, there's what we call lines of symmetry, which all of you know here. Maybe some of you might not know planes of symmetry. Well, planes of symmetry are just the same as lines of symmetry, but for them they are planes, as you can see here. This is an example of a plane of symmetry. That is, this is a plane or a plat in French, which is cutting this disc into half. Okay, symmetrical. Then even this one, the one in green, is also a plane of symmetry. The one in red is also a plane of symmetry. So according to principe de Curie, what we do is, for us to know the direction that E, because E will have 3 components, as I said, E will have 3 components. One in the X component, the other one in the Y component, the other one. But you want to make your work easier, because you know that instead of calculating all the components. So symmetry or principe de Curie helps us uh, nullify other components. For example, its components. So if you do the intersection of all these planes, okay, so if you see here, this plane, the one in blue, this plane is Z, this is Y, this is X, this is Z, this is Y, Y or Z, Y or Z plane. Okay, then we also have this plane in red, this is X or Z. So the other one is YZ, the other one is XZ. Then we'll have plenty of them. But if you find that the intersection, you just do the intersection according to how we find. If you want to know the direction, this is for a case for a disk, because a plan infini is considered to be is equivalent to a disk with of radius equal to infinity. Okay, so where was I? Where was I? Okay, I was here. No. So, so all concept of symmetry also applies to a plan fini. Okay, so for a disk, we consider that the intersection of all planes of symmetry is just if you do the intersection, or what is common to all these planes, you find that the z-axis is common to all the planes. So from here, we deduce that the only component E is only has one direction, and it's a z component, that the other components are 0. That's how we find the component. Okay, Then from here we can also say that E is a function of Z only. So Z is the only variable that E would depend on. So this helps us redo our calculations. Okay, so from now onwards, we will know that E is in the direction of Z through symmetry, and these are planes of symmetry. So I took this picture for you guys so that you are able to see what I mean by planes of symmetry, and if you do the intersection. So no matter the coordinate system, even the cylindrical coordinate system, E is always, if you want, you can sort of my exam that E is always using symmetry. E is always only has one component. Okay, I can tell you, give me the three components of E. Then from after studies of symmetry, which components will be zero or which component will be valid. So E, what we mean, E is only in the direction of Z. So it can be upwards or downwards. Now, let us now go to whatever applies to a disk also applies to a plan infinite, because we consider a plan infinite to have radius equals to infinity as demonstrated. Okay. Now, we're now using theorem de Gauss. Okay. So with theorem de Gauss, we use what we call, you'll be using this a lot, and the simplified calculations actually. So with theorem de Gauss is what we call a surface de Gauss. So this is an infinity plane or plan infini. Okay. So you can just put any surface where you are able to calculate its integral. So for example, for a plan infini, we always use a cylinder. Okay. So when using the theorem de Gauss, we use what we call a surface a Gauss surface, and a cylinder for a plan infini, a cylinder applies. Okay, so this is a cylinder. You position your cylinder like this. You draw a cylinder on the plane. Okay, then what does theorem de Gauss say? So if you remember, so now we're now trying to calculate for the plan infini. So this is this is an infinity plane. Supposons que ça c'est un plan infini. Then I'll draw a cylinder like this, which will pass through, which will cut through the infinity plane. Okay. We know that the charges are on this plan infini. So the only part of the cylinder will have the charge inside is this part. Okay. This is because the charges are on this plan infini, mind you, don't forget. So this part, in this part of the cylinder we don't have anything. In this part of the cylinder we don't have anything. The only charges that are inside are here. Then what does theorem de Gauss say? Theorem de Gauss says that the flux, so we use the definition of flux to find the show electrostatic. Don't forget, our goal is to get the show electrostatic, and we've just concluded that show electrostatic has one component that is in the z direction, that is it's on the z axis. Okay, so we use flux, and we learned flux last time, but I remind you. So flux, according to, and I also remind you of theorem de Gauss, we said that what Gauss said, according to theorem de Gauss, is a surface. What theorem de Gauss said is that the flux for a charge inside a volume, maybe inside this cylinder, the only charge inside this cylinder, maybe my diagram might not be clear. So this is the yellow part is the plan infini, and then if you put a cylinder that cuts through this plan infini, so the only part of the plan infini, the charge that will be inside, this is the charge. Then theorem de Gauss, what does theorem de Gauss say? Flux is equal to the charge inside Q in over what? Over epsilon 0. If you remember, we looked at this. Okay, so that's what theorem de Gauss. So we use theorem de Gauss. Okay, so but for now you know that if you put a cylinder on the plan infini, this is the charge. This is the charge that will be where? This is the charge that will be inside. So the charge outside you don't consider it, because the charge outside will give us what? Will give us 0. If you remember theorem de Gauss. Gauss said that if there's a charge outside and charge inside, the only charge that counts is the charge inside. And the flux, you find the flux by saying the charge in over epsilon 0. So this is why it simplifies the calculations, because the only charge, you see, you had an infinity plane of charges, but now you have used this is what we call a surface de Gauss, a cylinder, for example. Always use a cylinder for your plan infini, because the cylinder, you see why it simplifies the calculations. So you're going to use the theorem de Gauss, and theorem de Gauss, he talked about flux. Flux is equal to q in over epsilon 0. We did this, was another the whole topic last time. This is the essence of attending those other lessons that we're doing. But yeah, so if you have a question, you can stop me. You can just speak, because I'm not able to see the hands, but I hope you're following. Now, uh, the integral form of the general definition, or the integral form of flux. Flux, we just say flux is what? Flux is the integral on a surface. So we used to integrals. Then we said that it was the projection of E on the surface ds. So in this case, this is our surface, the entire cylinder. It's a closed surface. Okay, so this is a closed surface. We have the two circles, two discs. That is, if you've got a circle which has got which is closed here, it's called a disk mathematically. Then we've got the surface lateral in French, retro surface. So if you put this together, one, two, three, for people who are good at mathematics and used to calculate the total surface area, you might remember this. For a cylinder can be decomposed into this and this and this. This is a closed surface. So the surfaces that are put together and they form a volume. So at the, you can apply the theorem de Gauss. Okay. So for you to apply the theorem de Gauss, to begin with, you had a plane of charges. This plane of charges was not inside something. So you have to put them inside, and you have to use a surface that is going to be useful. That is a cylinder. So you're going to enclose part of the charges inside a cylinder. That's the first step after studying symmetry. And then you find that the only charges that will be enclosed is this part. Then you are going to apply the theorem de Gauss, which says flux is equal to charge in over epsilon 0, as simple as that. Okay, now uh, you also you're also going to be to remind yourself of the general formula of flux. It's the integral of, you first project E onto ds, then the total flux we sum up, or we integrate on a surface. So now if we're integrating on a surface, we use two integrals. If we're integrating on a volume, we use the three integrals. If we're integrating on a line, we use one integral, in that order, as simple as that. For example, if we had a wire, sometimes we won't look at this. We were supposed to look at this, but unfortunately, because of time, we won't look at a wire, but you'll find it in your school. For example, they might tell you to find, when you are working with a wire, you know that a wire is just a line. So for a wire, you're going to use one integral, E, then dot dl, because you're going to be dotting to the what? To the line. For here, we're dotting on a surface. So it's just the E and the surface. E dot ds, if you want to remember the formula. Okay, so the theorem de Gauss said we're using the theorem de Gauss in order to calculate E. Don't forget. So the flux, which is generally given by two integrals, E dot ds. So what is it equal to? It's equal to q inside over epsilon 0. How many minutes am I remaining with? Oh, like 18 minutes. So, and then, so this is what theorem de Gauss said. If you want, you can just alter this. The double integral of E dot ds is equal to q inside over epsilon 0. Okay, now, so you're going to, this will be the left hand side, and this will be the right hand side. So you're going to work with a left hand side, and you equate it to the right hand side. Okay, so we're going to start with the left hand side. This type of this double integral, we're going to um, decompose it further. So the integral on a cylinder, a surface is a cylinder. Okay, so a cylinder, as I said, has got two parts. The top part, a disc, the middle part, and the down part. Okay, so you have three surfaces. You can get three surfaces out of a cylinder. Okay, so your integral can be decomposed further into those three surfaces. Okay, that is, let's say, let me call this surface as S1. This is S1, and this is S2, then this is S3. Okay, and then um, when you're putting a vector to a surface, for example, S2 will have, this is the normal vector, the vector perpendicular to which will be in this direction. Then S1 it will be downwards like this, but perpendicular to it. Then for S3, this surface, the retro surface S3, will be, the direction will be in this side. This is how we indicate the directions of each surface. Okay, so we have up, down, sideways. Okay, up, down, sideways. These are the normal vectors. Okay, because that surface is a vector. Okay, so you're going to decompose this integral into three surfaces. So you're going to say we're going to integrate E on the first surface, that is D S1. Okay, plus we're now going to integrate E on the second surface, which is D S2, this surface. Then the third one will be the surface lateral, this surface. Okay, it was like curved inwards for you to make a cylinder. You know these things. Then the third surface will be E dot ds3. Okay, now the reason why we chose the cylinder, this is why we see the reason why we chose the cylinder, because the calculation simplifies. Okay, so if I were to ask you, and the reason why we had to know the components of E, we're from establishing that E is in the Z direction. Okay, and we use cut to indicate the Z direction. So E is in the Z direction. Okay, that is, E is either upwards or downwards, because this is Z axis. Okay, on the coordinate systems. Okay, either upwards or downwards. Now, another thing about the dot product, I don't know if you did this in Mécanique du Poids, but if you're dotting two vectors that are collinear or parallel, that's when you get an answer. If the vectors are not collinear, if the vectors are perpendicular, the answer is 0. Okay, let me apply what I'm saying. So E is in which direction? E is in the Z direction. What is our S1? S1 is in which direction? Yeah, S1 is in this. It's in the Z direction, just downwards, but in the Z direction. So this integral will be valid whenever we're dotting two vectors. Actually, here the dot is supposed to be here. Okay, whenever we're dotting two vectors, okay, you check the directions. This is why knowing the directions matters very much. So E, E is in the Z direction and S in the Z direction. So if the directions are the same, you keep that integral. That integral is valid. So this one, this one is valid. S2, I'm also going to say S2. S2, you are dotting it with E. Is E in the same direction as S2? Yes, S2 is in the Z direction. So now S2 to now this one, E is in the Z direction. Okay, E is in the Z direction, but S3 is in which direction? Perpendicular, if you see. So ama directions are payakan. The other one is in this direction. There's no, these two are perpendicular to each other. So this part of the integral will be 0. This is why we call this a Gauss's surface when applying the theorem de Gauss. The cylinder is important because you find that integrating on this surface will be 0. but we only have integrating on this surface and this surface, and these surfaces are just equal, they're just opposite in directions. So if you're able to find the integral on this surface, it's easier for you to find the integral on this surface. This is why a cylinder is very ideal when we're using theorem de Gauss. So don't forget, this is a integral form, and you decompose into three because your surface has got three components. And now you check which component is zero. Then you have these two for the discs, the bottom and top discs. Okay. Now E is a component of so whenever you do E dot ds, so the dot product also converts two vectors into one vector, into a scalar. That is, you will no longer have a vector. Okay. So the first part, this first part is going to give us E ds. That's how you move from a vector to non-vector because of the dot product. So you maintain the integral ds1 then plus integral. So E, you just multiply E ds2. Okay, and then the other one is 0. Okay, so how many minutes am I remaining with? 11. Okay, so here um E is only one variable dependent, only depends on one variable, that is z. Okay, now if you look at the s1, whenever we're integrating with respect to s1. At s1, the variable z is fixed. Okay, it's not changing. Okay, for the surface, s1 is fixed here, so the value of z is fixed also. So in short, this information is just to help you know that you're going to take E out of the integral, so you're going to have ds1. Okay, then plus E, then you even on s2 you're going to find that because E is only one variable dependent on z, and s2, the surface s2 doesn't depend on z, so it's going to be ds2. Okay, now if you look at the surface ds1 and ds2, these are equal. Okay, these are disks that are equal, so we're going to say, okay, before I even conclude that they are equal, so here E, when you're integrating the integration on a surface, the answer is just the total surface s1 plus, here when you're integrating on a surface, is going to be s2. Okay, whenever you're integrating on an elementary surface ds, it's going to be s1 s2. Now we know that s1 is equal to s2 from the diagram. Okay, so let's call this to be s. So E s plus E s, this is going to be what? 2 es, as simple as that. So we've established that the left hand side of the theorem de Gauss is simplifies to 2es 2es. Okay, now we're now going to deal with the right hand side. Okay, now when you have the only charge inside, the right hand side says q in over epsilon 0. Epsilon 0, ignore it, you look at q in. So the only charge, if you pay attention, the only charge that is inside here is also on a surface. This surface is equal to this surface s1 and s2. Let me call this surface s4. Okay, s4. Then there's a charge. This is the only charge inside. Okay, if you look at this picture, where is the picture? Where is my beautiful picture? Yeah, this one. This is the only charge inside. It's a disk of charges, if anything. It's a disk of charges. Okay, and it's also, this surface is equal to this surface, which is equal to this surface. Okay, let's now go back. Okay, so for our q in, it's on this surface, and they'll give you the surface density, which is given by sigma. Sigma is the surface density. So for you to know the amount of charge here, for you to know the amount of charge here on this surface, it's just q in will be equal to sigma multiplied by the surface, as simple as that. Now this surface f, we're going to go its surface this surface is S4. Now we know that S4 is equal to S1, which is equal to S2, which we're just coding S. So Q in will be equal to sigma S. As simple as that. Okay, so Q in. So this is how we move from, if you want to know a total charge is equals to the surface density. This is why I call it surface density, because for you to find the amount of charge, you're going to multiply by a surface where that charge is. So this is where our charge was. So if you've been given the surface density, so if you want to know the charge here, you just multiply by that surface density multiplied by the surface. As simple as that. So here on the right hand side, where there's Q in, I'm going to put the sigma S. And this S is equal to this S. And it's originally S4, but since it's equal to S1 and S2, which we just code S for our calculations to look nice. So the left hand side gave us this. The right hand side, from the theorem the gauss, who said Q in over epsilon 0. So where there's Q in, I'll find Q in, which is surface density multiplied by S over epsilon 0. So now I'm going to equate these two, I mean. How many minutes? Oh God, 6 minutes. Okay, we're there. So I'm now going to equate. Okay, so we're going to say 2E S is equal to sigma S over epsilon 0. So we know that this surface and this surface is equal. So we can now cancel. Well, now remember, what are we finding? What we're finding is E, show electrostatic. So we're going to make E the subject formula. So E is going to be equal to, so we're going to find that this and this will cancel. Sigma over epsilon 0 to epsilon 0. Therefore, ladies and gentlemen, so now we know that E is in which direction? E is a vector. So we now change this into a vector. And we know it's in the direction of Z. So we're going to say sigma over 2 epsilon 0. Then UZ, where UZ is a unit vector to show that it's in the direction of Z. Or this can be written as sigma over 2 epsilon 0 K. K is also a unit vector. You just add a unit vector because show electrostatic is a unit vector. Therefore, the show electrostatic or electric créé par un plan infini will be equal to sigma, which is the surface density, over 2 epsilon 0 in the direction of K. Okay, so that's how you find the show electrostatic using theorem the gauss. So this video is well recorded, so you can go through it to understand. I know there are some parts which you didn't understand, but it's a step-by-step video.